Alright team, I wanted to follow up with a little bit about the standard model and all that stuff we discussed last week that kind of, I think, left you all a little bit confused and maybe a little bit interested. Remember, when we talked about physics, we were talking about models way back in Physics 1, and we always said, you know, this model works and that model doesn't, and it breaks, or this one works here, but it only sort of works. And really, that's kind of the goal of physics in general, is to create these models, and we think we sort of found the model that works for all of everything. Kind of. And we talked about that last week, right? It has gravity and the weak force and the strong force and electromagnetism. And we think that that's it. And what you're looking at is pretty much everything that everything is made of here. This is the standard model. And you can see here the purple things are called quarks. And they're what make up everything. And you might be asking yourself, well, what the bananas? Like, why? Okay, I guess that everything is made of quarks. Well, just hang on a second. We're going to do something today, I hope, that kind of elucidates why these things need to exist. And you have these crazy things like up, charm, top, down, strange, bottom, and they're organized in rows and columns, sort of like the periodic table, but way, way, way smaller. So things on the periodic table are billions of times bigger than the things that we're talking about on this table, which is the standard model of physics. And then right here you can see that there's like a photon and a gluon and a boson and another boson. Like, these are all sorts of bizarre names for things, and what are they and what do they mean? And that's really what we're going to explore this week, because we're getting ready to go to Fermilab, where a lot of this stuff was discovered. And you can see here that we know some of these things, right? This is the only one I really recognize, the electron, and it has friends, the muon and the tauon, which are sort of bizarre, and then these neutrinos, which are even weirder. And these bosons next to them, I don't even know what they're talking about. So really I only recognize two things. I recognize this photon as a ray of light, and I recognize this electron as the thing you talked about in chemistry class. And so I think we should hang out with that a little bit today and play around. So what I'm going to have you guys do is pick a particle, and I'll show you a list in a second, and I want you just to become that particle's zookeeper. So imagine that you had a zoo, and you had to show people this exotic particle that no one's ever seen before. What do they need to know, right? What's the placard on the front of the cage while you watch your, beta pion eat a zebra carcass? So let me dig in a little bit more before we get going on that assignment there. For instance, a proton, which you know of as matter, is made up of two up quarks, so 1, 2, and a down quark. Why? We'll see. So we'll see in a minute. But that's the up and down of it, I suppose. Larger things are made of charm and strange and truth and beauty. You can see here they all weigh different amounts, right? Notice these units are nothing like what we've talked about in chemistry or in physics before. These are very bizarre small units for such small objects. But you can see here these ones are fat compared to these ones. So anyways, the standard model is kind of messy, and it seems kind of random that these are the only, 20 or so particles. Let's see, 1, 2, 3, 4, 1, 2, 3, 16 particles that make up all of reality. And you'll also notice here that there's no talk of gravity, right? Where's the graviton? Like, where's the thing that does gravity? This one does electricity and magnetism, right? These ones do the weak force. This one does the strong force. These ones are whatever they are. Where's gravity? Well, no one knows. So obviously there's another column here that we've never seen that has all the dark matter. And actually I'm hoping that there's a whole 70 million more columns so that we're not done learning about things. So anyways, let's talk a bit about what you're going to do. What I want you to do is go to the list of particles on the old Wikipedia, which is trustworthy, and I promise I haven't vandalized this, not even a little bit. And you can see here there's a list of a bunch of particles. You see here, these are the particles that we saw before. These are the neutrinos that are still on that original page. Here are some of the bosons. Here are some crazier things. But what I want to get down to are the, let's see, I guess maybe this is wrong, list of bosons. I'm going to give you guys some choices here. So I want you to become zookeeper, right? I want you to sort of create me, why can't I find a good list? Hang on. Create me a good, I don't know what the word is, exhibit, right? I want to walk through a zoo and meet these particles, and they're definitely bizarre. List of baryons. And here we go. This is what I'm looking for. So here are all the particles that exist, right? And so up until this time in your education, you've known about protons, neutrons, and electrons, and they make up everything. Well, that's absolutely not true, right? Here's the proton and a neutron, and then here's everything else. And so what I'd like you to do is come to the list of baryons. And at this point, you're probably saying baryons, boson, fermions. What does all this mean? Well, exactly. That's why I want you guys to play around with this. I want you to just muck around in the language of particle physics before we head to Fermilab a little bit. So I'm just basically throwing you in the deep end on purpose, right? And then we'll just swim our way out in any way that makes sense to us. So if you would, no one pick the same particle. Just put up on the board your name and what particle you want to do. One of you can pick proton and neutron, but if you do that, you have to do them both. Anybody else, you can pick one of the weirder ones, like, for instance, the lambda, right? You can see here that's made out of an up, down, and a strange quark. So that's a big, fat, fatty particle. And you can get down here into some of the really weird guys. The charmed double bottom omega, which is made out of a charm and a bottom bottom, which is a giant particle. And again, I know you probably don't have very much of any idea what I'm talking about. But go ahead and give these a whirl. If the baryons don't trip your trigger, you can switch to mesons. Okay, and the mesons are a lot like the baryons, except they're smaller, which is something that you also can dig into. So basically, your choice is completely random. Just basically pick a letter you like, is what I'm asking you to do, and then create this sort of zookeeper mentality for this guy. And I gave a list of stuff I want in your report to the sub. So mesons and baryons, hopefully you've seen that. So here are the things that I want you to talk about, right? I want you to give me its name, how it was discovered, and when, how does it decay, and what does that even mean, what type of particle it is, what lab discovered it, why does this particle even matter, what is its lifetime at rest, and what's its lifetime at 99% the speed of light. And now this is something that I'm going to talk about for just a couple more seconds, and then we'll be totally done with this video and you guys can get to work. We should have cart F, by the way. Oh yeah, and sorry I'm gone. I'm up in northwest Iowa at Okoboji, not having fun. I'm doing a workshop for a bunch of teachers up there. And I miss you guys very much, and I'd rather be working with you, of course, but you guys don't pay as much. So I'll, see you guys when I see you. Anyways, I want to get back to this lifetime at rest and lifetime at sea. During Physics 1, we talked for just un momento about things that live longer because they're moving faster, right? The twin paradox, right? If Quinn goes on a journey and comes back, he'll be younger than Bailey. Well, what does that mean? Well, it has everything to do with how fast their clocks tick because they're moving. And I'd like to show you a little bit of math to kind of get you to dig into that. And that's called time dilation. And I expect you to be Googling these things after I'm done with this video. I don't expect you to learn everything from me talking. But we're just going to use the Wikipedia like it's totally okay to do that, I guess, today. So here's the equation I'd like you to learn, and we're just going to talk about for 2 seconds. Right here, this equation, I'm not sure if I zoom in if the computer will honor that, so I'm not going to try that actually. This is the time dilation equation, which looks really fancy, but you'll actually notice that it's not at all very fancy. It has a square root in it, which makes it look cool, but that's about it. If you want to know how much longer your time is dilated because you were moving, all you do is stick in your speed here for v, the speed of light as c, and you multiply it by the time that you wanted, and this will make your time grow. Okay, and you can see here that here's a graph of how that equation is going to work. You can see here as you get closer to the speed of light, this factor for time dilation really blows up. In fact, it goes to infinity, which says that you can't get to the speed of light because then your time would slow down to 0 and you'd never get to the next second. And yeah, fantastic to say that. We'll talk about that, of course, again on Tuesday when I get back. So this is the equation. Go to the time dilation thing. You're looking for this. It's delta t over the square root of 1 minus the fraction v squared over c squared. And you notice here that that fraction looks fancy, but again, if you put in c for v, you get c squared over c squared, which is 1. You get 1 minus 1, which is 0. You get a some time interval divided by 0, which is infinity, which impossible to go to the speed of light. I just want you guys to play with this. Of course, we'll explain it and derive it and mess around with it on Tuesday when I get back. So all of that to say, when you're answering this question, what's its lifetime at the speed of light? Take its rest lifetime, stick it in for t, stick 99% the speed of light, stick that in for v, and you'll get a time dilation. Okay? So have fun with that. If you didn't understand what I just said, which is quite probable, feel free to read the Wikipedia entry or grab my modern physics textbook or Google how to do a time dilation problem. I'm sure you can handle it. This is one of the standards, so I'd like you to mess around with it. And your particular zookeeping of a particle, again, which is a meson or a baryon, that's going to go up on your WordPress blog as your competency for this unit. Great, so relativity, time dilation, baryons or mesons, pick a particle, have fun with it. The sub should have a list of things that you want to put in there. Make it a little more creative than my list. Again, I miss you guys a lot. I really like working with you. And yeah, have a fantastic afternoon and stay off drugs.